Awesome. Thank you very much for the introduction. So, yeah, it is windy up here in Cheyenne and the surrounding areas, and that's pretty much the motivation for this project. With strong winds, they're really common across southeast Wyoming and even portions of western Nebraska in the cool season, mainly from October through March, but can extend beyond that just a little bit. This past April was actually extremely windy across our area. So we have that, but then also we have two major interstates that run across our CWA, that being Interstate 80 and Interstate 25. And these interstates are some of the busiest highways with respect to truck traffic, according to the Wyoming Department of Transportation. And so a mix of these interstates, in addition to these strong winds, can cause frequent blowovers of light and high profile vehicles. You can see on the images on the upper left, we have one that's a truck actually being blown over onto a cop cruiser. There's a video of that can be found online, I believe. But then also the bottom right, just lines of trucks that have been blown off. This is just south of Cheyenne, I believe, on Interstate 25 due to those strong crosswinds. So definitely a hazard that we forecast pretty regularly across the area. So as far as previous work goes, this isn't the first study to try and develop local forecast tools for these high winds. I believe we even dug up some documentation while cleaning up the office of even studies dating back to the 70s on predicting high winds or using tools. So as far as some of the more recent ones, an early 2000s study looked at the correlations between height gradients and wind gusts at Arlington, Wyoming, and found that a Craig to Casper gradient at the 700 and 850 millibar levels was a pretty good predictor of strong wind gusts at Arlington, especially around a threshold of about 50 to 60 meters. And then a 2015 study developed a pair of logistic regression models to determine probabilities of exceeding high wind criteria gusts at two locations. That would be Bordeaux, Wyoming, and Cheyenne, Wyoming. And these models take multiple parameters. I believe the Bordeaux model was about 3 parameters and Cheyenne 5 to create these probabilities, which were then later refined to create specific thresholds that forecasters use regularly when making high wind warning decisions. So that's the current tools that we have, and so this most recent study was trying to find a way to kind of make an improvement upon those current tools that forecasters use. So here's a quick look at output from the logistic regression model at Cheyenne. And so in these data tables, all the rows highlighted in yellow show when that logistic regression met that optimal probability or exceeded that optimal probability, and therefore high winds would have been predicted by a forecaster most likely. And then the red highlighted cells show when high wind criteria or high wind gusts were met, and that is shown in peak gusts in knots. So over 50 knots is that threshold. So did a pretty good job in this case, but there are other scenarios where forecasters have identified that maybe there's room for improvement, and so that's where the study comes in. So looking at our study domain, here's a map of all the counties within our forecast area with select cities labeled, and our 3 main locations for the study are shown in red there. There's Arlington, which is along Interstate 80 between Rollins and Laramie, and that's typically subject to gap winds, but can also be impacted by mountain wave activity or even some downsloping winds. There's also Bordeaux, which is north of Cheyenne along Interstate 25, which is also another major gap area, but could also experience downslope winds. And then there's Cheyenne, Wyoming, kind of right at that intersection of Interstate 80 and 25. So those are our 3 main study locations for this project and developing tools for high wind prediction.
Okay, so looking at some climatology for those 3 sites of interest. So what you're looking at here are heat maps. So on the x-axis, you see the hour in Zulu time, starting from the left at 0Z. And then you have the months on the y-axis. So the top row there is March, and the bottom row is October. And the warmer colors are indicative of a greater frequency during those times. So if we look at on the left one there, Arlington, there's really no true temporal tendency for Arlington as a gap area. Pretty much any time of day can be favorable for that area. Bordeaux's much the same, but there is a little bit more of a greater frequency as you get into kind of the afternoon hours. Cheyenne is definitely more favorable overall during the afternoon. And I do want to note the scale change there at Cheyenne. Cheyenne has much fewer cases overall for high winds than as compared to Arlington and Bordeaux. We have a lot of days where we're 45, 50 miles per hour, but exceeding 58 miles per hour is not nearly as frequent as Arlington and Bordeaux. But we do see that all sites have a climatological peak between November and February, and that kind of helped us define the winter months for the study from between October and March. So for those of you that aren't familiar with gap winds when it comes to mountain meteorology, gap wind, put simply, is an area of enhanced low-level flow resulting from a gap in a mountain barrier. It results from a tight pressure gradient across the gap, and in cases where you happen to have a major highway that runs directly parallel to that gap, can certainly create a significant problem for commercial truck traffic. Just a simple map here, gap areas across the Cheyenne forecast area in southeast Wyoming in particular. Each arrow represents a gap of varying sizes, pretty much all over the place. So definitely a big problem for us in our forecast area. And this is a Google Street View of the Arlington gap. So just to give you an idea of what one of those mountain gaps looks like. So for observational data, for highway sensors, we got the data from Utah Meso West, and for ASOS sites, we got that from we got those archived METARs from IEM, or the Iowa Environmental Mesonet. We collected data from October 2010 or the start of the record to March of 2020 at varying temporal frequencies. So some sites may have been 2-minute data, others 5, and there were some sites that we looked at that only reported every half hour to an hour. Observational data, we gathered wind speed, direction, and gust. In the case of ASOS sites and the METARs, even with 5-minute data, we found that the instantaneous wind gusts would often not capture the peak wind for a given time range. So we had to gather the peak winds for those. Generally speaking, though, for highway observations, those observations were every 2 minutes or so, and it wasn't nearly as much of a problem to capture the strongest wind gusts. So we ended up calculating maximum 1-hour sustained winds and maximum gusts, and we looked before and after 90 minutes before and after of 3-hourly time intervals, 12Z, 15Z, 18Z, and so on. Reason for that was to get kind of a standardized observation time, as well as working with time matching with our predictor data, which I'll talk about in just a minute here. We also classified our observations into 3 categories. We have the none class. you may think max gust of 40 miles per hour, that's still pretty windy, but by Cheyenne standards, definitely not as significant for us. So gusts less than 45, none class. You can think of elevated as kind of your special weather statement or wind advisory type criteria, where you're in that 35 to 40 mile per hour range, gusts starting to approach high wind criteria. In Cheyenne, we actually don't do wind advisories because we have them out pretty much in the entire winter. But also we have the high wind class, which is our local criteria, and I think is probably the common criteria across the board, with gusts greater than or equal to 58 and sustained greater than or equal to 40. Predictor data was gathered from the NARR, North American Regional Reanalysis. Gathered that for that same 2010 to 2020 time frame every 3 hours for the winter months only. Extracted data, gathered all your basic stuff, your sea level pressures, winds, heights, temperatures, omega, cloud cover. We also looked at various forms of derived data, different height gradients that we already knew about, like the Craig-Casper gradient, and we also analyzed the terrain and synoptic climatology to come up with some other gradients to experiment with. Computed lapse rates, sea level pressure gradients, and also vertical potential temperature gradients as well.
So we took all this data that Chris just mentioned, and for this project, our new tool that we're developing is a random forest model. So the next few slides will kind of explain that really quick. So I'll start with kind of more of the base of that is a decision tree. And so here we have a decision tree. This is just 3 decision points, so kind of a little more simpler one. And what the model does in the training process is it will create a decision tree. It'll select a predictor variable as well as a threshold of that predictor variable that can best isolate the labeled classes that Chris was just mentioning. And so in this case, we have the Grand Junction to Cheyenne mean sea level pressure gradient if it's less than 5.2 millibars. So if that's true, we have data moving down to the left, and if it's false, we have data moving down to the right. And then the next predictor is then randomly selected that can best isolate those non-classifications from those high wind classifications from those elevated classifications. And so you get down to the point where then a forecast is made at these leafs down at the bottom, what are called leaf nodes. So that's how the kind of training process works, by looking at the training data and tries to best isolate those classes. And then in the testing data set, this is all unseen data from the model that then is fed into all these decision points down to a bottom leaf node where a decision is made. So this could be, stuff from our testing data set or brand new forecast data, which we were doing in real-time operations right now. So that's kind of your decision tree with a maximum depth of 3, which is just 3 decision points. So bringing that to the next level, that's how we create a random forest. It's pretty much an ensemble of decision trees. So in the training process, we create many different, or the algorithm creates many different decision trees, and they're all unique using different predictors at different stages of the tree, as well as different thresholds to best isolate the data. And then when the new data, testing data, is run through all these decision trees, they pretty much vote on which class is most likely, or which class is predicted. So in this case, we have a random forest made up of 6 trees. Each of them have a max depth of 3. And if, in this case, 3 of the 6 predict high wind, then we would get a deterministic prediction from the random forest of high wind, and a probability of high wind of about 50% in this case. Now it's a little bit more complex how it comes up with those probabilities, but that's the general idea. And so this is all looking at it in a classifier framework, so based off of those classes that we defined earlier. But there's also a regressor that we'll talk about more, which actually predicts wind speeds using this same method. Now, the random forest, it can get complex really fast. So here is a look at a one decision tree within a random forest that has a maximum depth of 20. So a lot of different decision points, a lot of ways the data can fall in. And then if you, let's just say, have 100 of these within your forest, you have 100 just as complex decision trees. And if we kind of look in a little bit closer, we can just see how many decision points there are, and even to the point where you get only a single sample from your training data set that goes out to a leaf node. So you only have, one data point supporting that decision, which isn't very good. And so that's where there's a lot of balance here of trying to make a random forest, or the decision trees within your random forest, complex enough to predict your data, but also not too much to the point where it really learns your training data and might be not as useful for any new data that might be seen. So there's definitely a balance between making, growing out your trees, but making sure you prune them a little bit as well. So as far as our setup for the random forest, we had 10 years of data that Chris mentioned, and so we used the first 8 years for training. That was to create all those decision trees within our random forest, and then we tested on the final 2 years. So we'll show some verification statistics from that. As far as our random forests, they varied from 150 to 200 trees within each forest. And also one thing I want to note, we did not create just one forest. We created one for each of our 3 sites. So it's not one universal random forest for all those prediction sites. Each decision tree had a maximum depth of 10. And we also had class weights for the random forest classifier that would help the model predict high wind, or know that high wind is more important to predict than the other classes, since that is our goal. So it pretty much would, in the training process, penalize the model for not predicting high winds correctly. As far as the NARR predictors, we selected specific predictors for each model and unique to each model that Chris will explain the process for that here in a few slides. But we came out to about 20 to 30 predictors for each of our random forest models. So like I mentioned earlier, we had 2 different random forest models actually for each site. We have a classifier model, which predicts those labeled classes of high wind, elevated, none, in addition to a probability or confidence of each of those classes occurring. And so this is maybe a little more similar to kind of a yes-no decision on whether or not high wind warning might be needed if you're specifically looking at the high wind prediction, with probabilities attached as well. But then there's also the random forest regressor. And so that current version of our random forest regressor actually predicts the maximum wind gusts over a 3-hour period. And this provides additional details on the magnitude of the winds and most likely timing of those strongest winds. And it nicely complements the random forest classifier to help forecasters look at potential wind speeds for an event, but also communicate that information to the public and core partners.
So in terms of determining the predictors, one of the major things that we did was we analyzed each potential predictor individually. So what we did was we took each individual parameter and we ran them through several different thresholds. And then basically we said, okay, if we only use this parameter at this threshold and we hit that threshold and we said, okay, we're going to issue a high wind warning now, how would that single parameter do for high wind prediction? So we did that for basically everything that we extracted and derived, and we created these heat maps. So the example here, these are both for Arlington, and on the left-hand side, you see the 700 millibar height gradient thresholds. So on the left-hand side, you see several different gradient orientations. Since gradients are particularly important for gap areas. Won't go into detail about what each gradient is, but we can see that, so as we hit different thresholds there on the x-axis, as you get into the deeper blues, that indicates a better CSI score, a better forecasting score for those gradients. And we can see that the Craig to Casper gradient at around 55 to 60 meters was one of the better thresholds, as indicated by some of that previous work from that early 2000 study that Matthew mentioned earlier. And on the right-hand side, we can look at different levels for the Craig to Casper gradient. And in that case, we see kind of a nice little cluster of some higher CSI scores, kind of right in that 775 to 720, 750 or so millibar Craig to Casper gradient. So these heat maps really allow us to easily visualize the strongest parameters and the corresponding pressure levels. Now, it just so happens that gradients have a pretty strong correlation as it is for maximum wind gusts, especially for gap areas. So this all works out really nicely because you have that correlation. The CSI score analysis works great. But there are other parameters like, say, for instance, lapse rates and also omega. So lapse rates, just because you have steep lapse rates doesn't necessarily mean you're going to have strong winds, or just because you have subsidence doesn't mean you're going to have strong winds. But that also doesn't mean those parameters aren't necessarily important, because when we start to combine those with other parameters, we can see that, okay, lapse rates are important. You look at Cheyenne, we have a greater frequency in the afternoon, so lapse rates come into play. And if you have otherwise favorable conditions, subsidence gets to be extremely important as well. So looking at feature importances for each site, I won't go into too much detail here, but there's several different types of parameters that kind of make repeat appearances, different height gradients in particular, different omega levels, and also lapse rates. Those are kind of your big three for wind prediction that are common among all three sites here. The top predictor for Cheyenne has 650 millibar omega. When we analyzed the data, we actually found in our entire testing or training data set, Cheyenne actually never had a high wind case where the omega value was not indicative of subsidence. So just giving a little credit to the feature importances depicted here.
So we'll show some verification here in the next few slides. But as far as our verification methods go, with the random forest classifier, we used standard probability of detection, false alarm ratio, critical success index. And we did this in two different ways. One was looking at the exact times, and one was looking at more of an event-based approach. So if we look at the red highlighted box down below, if we use the one method, which was just looking at single observation times, that first row in that red highlighted box is an observed high wind, but predicted elevated. So we would have had a missed event. Versus the other, the next one down, we observed elevated and predicted high winds. So that would then be a false alarm in that type of verification. However, us as forecasters, timing's important, but we can, when we're issuing warnings, we're issuing it for a longer duration period, most likely. So we created this other verification metric of trying to group together multiple times together to create more of an event-based approach. And so in the red highlighted box there, since we did have an observation of high wind within a close period of time of a prediction of high winds, this event would then be considered a hit. So as far as our classifier verification goes, here we show performance diagrams for the single observation based approach, which is on the left, and event based approach on the right. These random forest models are shown in these circles, and the previous operational tools that we presented on earlier with those logistic regression models or just using Craig de Casper gradients are shown in the plus symbols. And so just a quick little walk through this diagram. You have probability of detection on the y-axis, and you got success ratio on the x-axis, and then your color fill is your critical success index, which is maximized in the upper right-hand corner. So as we move from the operational models to these random forest models, we can see with almost all, there's a general trend towards the upper right-hand corner of the diagram, showing that there is an overall improvement using these random forest models compared to previously developed guidance. And these are all statistics based off of our testing data set. So those final 2 years of our testing data set. So now more on the regressor.
Okay, so with the random forest regressor, on the left-hand side, you see these stacked bar plots indicating wind gust error for all sites in our testing period for winters 2018-19 and 2019 through 2020. So on the left-hand side, the top bar for each site is for all classes, and then you have from top to bottom, high wind, elevated, and none for your observed wind class. So the bar on the far left with the dark blue is what we considered an excellent forecast, where you had less than 5 miles per hour of error for that percentage of the time with those observations and forecasts. And the light blue is within 5 to 15 miles per hour, and then the red-orange was what we considered a bad forecast, greater than 15 miles per hour for error. So the blue colors for all classes especially, one thing that we thought was quite encouraging was all models fell within 15 miles per hour of the observed wind gusts, approximately 80% of all forecast times. As you might expect, though, wind speed forecasts do generally become less reliable as the event intensity increases. That's really not all that surprising because as windy as these places are, there's pretty limited training data at more significant wind speeds, especially as you start getting above 75 mile per hour gusts or so. And if you look at Cheyenne in particular, the middle bar chart. So you look at none, really pretty much your smallest bar for your bad classification there. But you get to elevated, and then you get to high wind, and then you're getting a lot more cases where you're getting greater than 15 miles per hour of error. So on the right-hand side, we have a chart for kind of indicating predictability by event intensity. Just an example from Bordeaux. This is a hex bin. It's basically a scatter plot with hexagons. So the deeper blue colors basically indicate that there are more scatter points within those hexagons. And in a perfect world, we would want those deeper blues to follow that 1-to-1 line, or that y equals x. So it gives us a really good idea of kind of the bias of the model. And overall, Bordeaux does perform pretty well overall through the testing data set there. But overall, this was pretty encouraging, and we definitely think that this regressor output could potentially be implemented into a GFE tool for first guess wind forecasts, or also be used potentially as an NBM nudger for specific locations. So getting into some case reviews now. So looking at March 28th, 29th of 2021. So we've got the surface on the left, 700 millibars on the right, March 28th top to 29th on the bottom. We did note tightening height and surface pressure gradients in the morning of the 28th. So that quickly became favorable for our gap areas. And then as we move forward in time, we started seeing that 700 millibar flow exceeding 50 knots over much of southeast Wyoming ahead of a surface cold front that was stemming from a surface low over the northern plains. And that transitioned this event more into a BORA type event. If you're not familiar with a BORA, it's basically just a cold downslope. Same general process as a Chinook, but the source region of the air moving over the mountain barrier is too cold to result in a significant warming effect. So it's seen as a cold downslope wind east of the mountain barrier. And also not shown here, but Wyoming was in the right front quadrant of an approaching upper jet, which helped give us the subsidence that we needed. So this was actually the first case we examined using GFS data as input into the random forest models. So give me an idea what you're looking at here. So the red line is the probability from the classifier of high winds. The orange line is the elevated probability, and the green line is none. The larger scatter points you see along the thicker red line, that is the classifier, the predicted class from the classifier model. So once again, red would be your high wind. And then the smaller scatter points are your observations. So we can see that overall, the model predicted timing of elevated high winds extremely well. And also on the right-hand side, we've got this rainbow of colors of the high wind probabilities. This is actually several different runs of the GFS, and we can see that the model has consistently predicted high winds at Arlington over several cycles, even as far as 5 days out. So that was really encouraging, and this information is available to forecasters in real time, so they can see what the trends have been. Other information that forecasters can see, changing that right image there, we have time series plots of individual parameters, and we can plot those against the distribution of the training data set. So forecasters can see kind of how those parameters relate to, say, for instance, other high wind cases that have occurred in the past. And we also have this SHAP waterfall plot, and basically this is based on game theory, kind of a coalition type game theory where each team member has different strengths to complete a common goal, and then those strengths though are disproportionate. So trying to determine how each team member or coalition member would contribute, and we can apply that same concept here and see which parameters are driving the probabilities up, or perhaps even driving the probability down. In this particular case, we see that the mid-level lapse rates and the Craig-Casper gradients were among the highest for Arlington in this particular case. And we look at Bordeaux and Cheyenne. So there is one more line for the Bordeaux here that you didn't see for Arlington, and that is the work BRX, work Bordeaux. That's the logistic regression model for Bordeaux. And the highest probability there was predicted too early in this particular case. So that probability was already on its way down when the random forest classifier was kind of on the uptick there. So predicted the timing fairly well compared to previously developed guidance. Did kind of miss the latter part of the event there with several observations 3 to 6 hours later. But overall, the Bordeaux model did a pretty good job. And then Cheyenne, wind probabilities were pretty low, but they did peak at the time high winds occurred. So that was pretty encouraging. One thing with Cheyenne, because of the limited number of actual high wind cases, it's really tough to differentiate those elevated wind cases from high wind, from that high wind events.
So I'm just going to show 2 more quick cases. This is going to go back to the testing data set, and then Chris is going to show one for the regressor from actually just 2 months ago, so this past winter. So this is, again, going back to using the NARR data in our testing data set. And so here's one case that we believe that the forecasters could have really benefited from using the random forest models in operations compared to kind of the more traditional forecast guidance that was available. So these are similar plots to what Chris was showing. And then the very top is actually kind of a timeline of our high wind warning for these sites and the different VTEC actions that were made. And so this highlighted area generally gives a look at what the initial start and end time of the high wind warning for Arlington and Bordeaux. And if you look at, kind of ahead of the shaded area and behind the shaded area, you definitely have high wind occurrences. So maybe this wasn't the best initial start and end time of a high wind warning. And you can also see up in the VTEC action, there's an extension to start it earlier, then there's a few other extensions to extend it out in time. And so, this is no knock on any forecaster because, if we look down at our logistic regression guidance that was being used at the time, it did not provide any high probabilities at all there for Bordeaux and definitely not for this kind of second peak in winds. However, the random forest guidance did provide better prediction for high winds and better timing prediction of high winds, suggesting it would start earlier than what previous guidance and our current warning started at, as well as continuing longer beyond the initial end time of the warning. So this is kind of showing the benefit of how this could have aided in a forecaster's warning decision making, because a better initial warning timing would then lead to better warning communication to core partners and get messaging up on the interstates to provide travelers with better timing on high wind occurrences. So one other case to look at. So this is what we would consider probably one of the worst misses by the model within the testing data set. And you can see in the red highlighted box, we had 4 time periods that observed high wind. However, the prediction was none. And even the probabilities were near 0 for high wind. However, we saw gusts around 60 miles per hour for an extended period of time. So this is one that Kirsten and I definitely were scratching our heads at, why is the model doing so bad? Until we looked at what the surface analysis was for this event. A nice Colorado low in March. You got tight gradients over the area, but it's definitely not a traditional orientation for a high wind event. But this map is more suggestive of a nice blizzard event across our area. So this was actually the bomb cyclone that year. Sorry, that's labeled 2020 on the bottom. That should be 2019. But yeah, this is a bomb cyclone of March 2019 that led to some significant flooding across eastern Nebraska, but brought a ton of snow to our area as well as high drifts, as you can see looking back at our office. So this was actually one that we were actually pleased to see, though, because we looked back in the testing data set and there was nothing similar to this in the testing data set for the model to learn off of. So if there's nothing similar for it to learn off of, it would have no business actually predicting these high winds. So this is the type of information that Chris and I have been diving into, some of these worst, the best hits or the worst misses, to relay that information to our forecasters to know kind of the failure modes of this model.
Okay, and really quickly here, going over a regressor case from mid-February, 17th through the 20th, so it's kind of a prolonged event. So on the left-hand side, you got the 500 millibar analysis at 12Z on February 18th. So we've got a strong shortwave over the northern plains. So this pretty much set up our low-level gradients to start getting our gap areas going early on in the event. And then on the right-hand side, we have the surface analysis at 0Z on the 20th. And we can see we're starting to get more of a west to east pressure gradient over the Rockies, which started to increase our winds further along our Laramie Range, just west of Cheyenne, and also locally into Cheyenne. So just to recap, Regressor is predicting wind gusts. So pretty much the same thing you've been seeing before, but no probabilities this time. The back shading indicates the observed or the predicted wind gust classes. So are you in the none? Are you in the elevated? Are you in the high wind category? And then the red and the larger scatter points, once again, are the classifiers. So we can kind of compare how the regressor is doing compared to the classifier. So on the upper left, we have Arlington. We can see overall the model did excellent with maximum wind gusts, overall timing. You get that little lull there after that initial push of high winds, which we think was still correctly suggested by the model. I mean, you're still predicting maybe a little bit too high of gusts, but it definitely predicted that decrease extremely well. But then late in the event, captured the end of the event really well, and then as we transition back to the none category. On the lower left, we have Bordeaux. Now, this is a very extreme event. The model did miss out early on. Did have a few high wind gusts around the same time that Arlington peaked up for the first time. So missed event by the classifier that predicted the none class. But we do notice that the regressor did kind of touch the elevated category. So even though you had that none, you had that little confidence boost from the regressor that you could at least have some higher wind gusts. As we look a little further off in time, the peak gust timing was predicted extremely well. Overall, the gust intensity was predicted pretty well too, kind of that 65 to 70 mile per hour range. But in this event, we had a 95 mile per hour gust that was not captured well at all. And this was the result of mountain waves. And mountain waves are notoriously difficult to predict, especially when it comes to gust intensity. So wasn't really a surprise to see that. But overall, the model did a pretty good job. And then for Cheyenne, this was on the right-hand side. Cheyenne actually did not hit high wind. I think our peak gust for this event was only 56 or so just under criteria. And neither model predicted that, so that's good. But even though we still had none off the classifier, we did kind of touch that elevated category with the regressor. So definitely a nice tool to complement things there. So overall strengths, timing, very well forecast by all models. in this event, high wind forecasts generally had a very low FAR. If it predicted high winds, generally speaking, it hit. And it also just some general success predicting elevated wind gusts when the classifier did not. General weakness would be more complicated factors like mountain waves, but overall with this particular event, no major weaknesses there.
So we're just going to show some initial verification from this past winter and wrap things up. But overall, it did a pretty good job over the course of October through the end of March. And so here's some statistics in a table for each of the 3 sites of POD, FAR, and CSI. And this was looking at using the GFS data in the short-term window. So anything that was a forecast lead time of 12 to 36 hours, which is kind of roughly where we'd like to be issuing our high wind warnings or watches. And these stats are then compared to, in parentheses, those advertised statistics from the NARR. And then and everything in green is better, everything in red is worse. So overall, the Arlington model did better than advertised for this event, with actually a much higher POD than what was advertised. The Bordeaux model was slightly worse, but if you look at the numbers, kind of make a comparison, it's not too far off from what was advertised using the NARR. And then the Cheyenne model definitely showed the worst performance over the course of this past winter. But however, as Chris kind of mentioned, there are times where it might not have predicted high winds, but there is, a spike in those high wind probabilities or high elevated probabilities that a forecaster could key in on it. And that's the most important thing too is, this is the model's performance, but how did we do as forecasters with our high wind warnings across Southeast Wyoming? So this table on the right is showing the same statistics in addition to lead time for our high wind warnings this past winter compared to, in parentheses below, the average from the previous 3 winters, and across our CWA as well as the respective zones for each of those sites where those models were created for. Overall, lots of green there, big improvement. And even for Cheyenne, we can see a much bigger improvement in lead time as well as some of the other skill scores. So, it's nice to see that, forecasters are taking the information from this model and using it successfully in operations. So, some conclusions, overall, the random forest models that were developed, both the regressor and classifier, definitely were improvement over previous guidance, and forecasters have shown confidence and grown to learn to use these tools to improve high wind warning decisions across our area, and use this information to improve some of our messaging and social media graphics or DSS packets when trying to relay the possible wind gusts that could be seen within event. And future work, that's just a lot of things that we are currently actually working on, such as exploring additional forecast parameters, such as time-dependent variables, and that's something we're probably going to be including with a new version of the model for next winter. One of the most important ones we found is, not just what is the height gradient, but what is the tendency of that height gradient over the last couple hours? Is it tightening? Is it weakening? So that's something we've been investigating many events to try and identify those best hits, worst misses, FARs, to help communicate that information to our other forecasters in the office, when it might be good to use, not so good to use, but also identify ways that we can improve the model, adding certain new parameters to the model. And other things, we started expanding to additional wind-prone locations across our area, as well as Chris mentioned GFE tools that could be used in the future, or even a hazard service recommender tool using this model output to recommend watches and warnings for high winds in the area. So just want to leave with one last thought about machine learning and AI and forecast operations. I came across this paper recently from Brandy Chase and co-authors down at the AI Institute for Research on Trustworthy AI in Norman, Oklahoma. And kind of the motivation for this paper is kind of they're looking at what are the 3 requirements of a good forecast? So the forecast one needs to be consistent with the user's prior knowledge, have good quality or accuracy, and be valuable. And this is all off of Murphy 1993 of what is a good forecast, kind of a little paper there and weather and forecasting. And so with this model, we have shown that it has good quality. It's an improvement over previous forecast tools that we've used in operations, and it is valuable. Our forecasters have used this tool to make an improvement to our products and services, as well as communication to external partners. But the first one, the paper kind of addresses that, if AI and machine learning methods such as like what is a random forest, if those things are kind of confusing to the user, then it could be difficult for the forecaster to achieve this first requirement of a good forecast. And so, this is kind of their goal, is to try and help, as they mentioned, they intend to write this paper to be a reference for meteorologists in order to make the black box of machine learning more transparent and enhance user trust in the model. Because if I just give you a random model, you have no idea what it is, and it just says to predict this, it might conflict with your prior knowledge. And so also understanding why it's coming to a certain conclusion is good information as well, like Chris was showing with those SHAP values, kind of trying to dive deep into why a model is making a decision like that. So we definitely encourage anyone who's interested to try and look up this paper, and it definitely provides a resource for certain types of machine learning to understand some of those algorithms if you're using anything at your local office or other tools that online that you come across. So yeah, we'll leave it at that and take any questions you guys might have.